Chapter 5. The Fine-Tuning of the Universe. We begin with a thought from philosopher and theologian William Lane Craig. The fine-tuning of the universe for intelligent life is so improbable that it cries out for an explanation. And as theoretical physicist Leonard Susskind notes, the laws of physics seem peculiarly suited to the existence of life. If any one of about 20 physical constants were off by even a small amount, the universe could not sustain life as we know it. The existence of the universe and its intricacies is a profound mystery that continues to captivate humanity. One approach to exploring this mystery is through the principle of causality, the logical idea that every effect has a cause and that nothing comes from nothing. However, this principle presents a paradox. If the universe had a cause, then what caused that cause? While some posit an infinite regress of causes, such explanations fail to account for the ultimate origin of the universe we now see. Importantly, for the purposes of this chapter, and indeed this book, I put aside speculation about what preceded the singularity or the Big Bang because it changes nothing in terms of the creation event at the Big Bang, which remains my central focus. Recent scientific advancements suggest the possibility of other Big Bangs previous to the one we now see, not just the one that birthed our universe. While these ideas hold significant implications, they do not change the core of our investigation. Whether our universe was part of a broader multiverse, other previous Big Bangs, or the result of a single unique event, the Big Bang remains a definitive beginning point for our observable universe. At the singularity, where time and space as we understand them cease to exist, all known physical laws break down. The universe transitions from a state of infinite density and no dimensions to one of expansive time and space. This moment, often referred to as the new beginning, transcends human comprehension and resonates with the reflections of some of the greatest minds in science. Stephen Hawking, who extensively explored singularities, observed, "The universe would not be arbitrary but would be determined by a set of laws. These laws may have originally been decreed by God, but it seems that he has since left the universe to evolve according to them." The singularity, whether viewed as the result of one Big Bang or part of a larger sequence, underscores the profound complexity and mystery of the universe's origins. This leads naturally to the concept of fine-tuning, the precise calibration of physical constants and laws that govern the universe. Fine-tuning refers to the extraordinary specificity of these constants, which, if altered even slightly, would render the universe incapable of supporting life. This apparent precision has not gone unnoticed by leading scientists. Physicist and cosmologist Paul Davies remarked, "There is for me powerful evidence that there is something going on behind it all. The impression of design is overwhelming." Similarly, Stephen Hawking also observed, "The laws of science, as we know them at present, contain many fundamental numbers. The remarkable fact is that the values of these numbers seem to have been finely adjusted to make possible the development of life." Astrophysicist Fred Hoyle famously stated, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature." These reflections align with the idea that the universe's fine-tuning is not a product of random chance, but a phenomenon that suggests purposeful design. Even scientists who refrain from drawing creation event conclusions recognize the problem of fine-tuning. Theoretical physicist Alan Guth once remarked, "The apparent fine-tuning of the constants of nature to support life is a problem that is recognized by all physicists." This statement captures a profound and widely acknowledged mystery at the heart of modern physics and cosmology. What Guth refers to is the observation that the fundamental constants of nature, the values that govern the behavior of forces, particles, and the structure of the universe, appear to be calibrated with astonishing precision to allow for the emergence of life. If any of these constants were even slightly different, by just a fraction of a percent, the universe as we know it would be inhospitable to life. Stars might not form, chemistry might not function, and complex structures like galaxies, planets, or living organisms could never emerge. This extraordinary balance has prompted many physicists and philosophers to ask, why do the constants have the values they do? Is it mere coincidence, a necessity of deeper laws we don't yet understand, or evidence of design? Guth's comment reflects the fact that, regardless of one's interpretation, whether naturalistic, multiverse, or theistic, the fine-tuning problem is not speculative or theological in nature. It is empirical. The constants are what they are, and the probability of their life-permitting range appearing by chance in a single universe scenario is vanishingly small. Once again, we must reflect on the singularity and the Big Bang, which initially offered potential. Yet it is crucial to recognize that this was not a passive potential. The true beginning offered only potential, but that potential, in essence, caused our reality. It was a loaded potential, containing within it the specific mathematical instructions and physical blueprints required to bring forth a structured cosmos. This potential did not simply remain abstract, it acted as the invisible architect that unfolded into a universe remarkably fine-tuned, where the precise conditions necessary for life and complexity were realized against seemingly insurmountable odds. In this sense, the potential was the seed, and the reality we inhabit is the inevitable bloom of a perfectly designed core. The fine-tuning of the universe manifests in numerous ways, from the fundamental constants of nature to the specific conditions that make life possible. The constants of the universe are like the fixed rules or settings that govern how everything works, from the smallest particles to the largest galaxies. These values don't change and are the same everywhere in the universe. They make sure that the universe runs smoothly and predictably. Without these constants, the universe wouldn't look anything like it does now. Stars, planets, and even life might not exist. The cosmological constant controls how fast the universe is expanding. If it expanded too fast, galaxies wouldn't form. If it expanded too slow, everything might collapse back in on itself. Even at the tiniest level, constants like the charge of an electron and the mass ratio between protons and electrons allow atoms to stick together and form the molecules that make up life. It's as if the universe is perfectly calibrated to support life. Scientists and philosophers often wonder why these values are exactly what they are. Some suggest it's just a lucky coincidence. Others think it's due to some yet undiscovered law of nature. However, if looked at objectively, it points directly to the work of a creator who designed the universe with meticulous care. Consider the cosmological constant. This value represents the energy density of empty space, often called vacuum energy, and functions as a built-in property of space that causes it to expand. Scientists associate this with dark energy, the mysterious force causing the cosmic expansion to speed up rather than slow down. The observed value of the cosmological constant is one of the most staggeringly finely tuned quantities in all of physics. Scientists estimate its precision to be accurate to 1 part in a 1 followed by 120 zeros. To put this unfathomable level of precision into perspective, imagine firing an arrow at a target located 1 trillion light-years away and somehow hitting the exact, microscopic bullseye. This analogy illustrates just how delicate the balance of this value must be for the universe to exist as it does. If the cosmological constant were even slightly larger, the universe would have expanded so rapidly after the Big Bang that galaxies, stars, and planets would never have formed. On the other hand, if it were slightly smaller, the universe would have collapsed back in on itself instantly, preventing the development of any complex structures. The precision required for this constant to fall within the narrow range that allows for a stable and life-supporting universe is so extraordinary that it completely challenges our intuition about randomness or chance. The gravitational constant is another fundamental number that determines the strength of gravity, the force that attracts objects with mass toward one another. While its precise value is extremely small, its impact on the universe is profound. If gravity were even slightly stronger, stars would burn through their fuel much faster. Stars rely on a delicate balance between gravity pulling inward and the pressure from nuclear fusion pushing outward. A stronger gravitational constant would compress stars more tightly, accelerating the rate of fusion. This would shorten the lifespan of stars drastically, leaving insufficient time for planets to form and for life to evolve. Conversely, if the strength of gravity were weaker, it would fail to trigger nuclear fusion in stars at all. Fusion is the process that powers stars and produces the elements necessary for life, like carbon and oxygen. Without it, stars would fail to ignite, and the universe would remain cold, bleak, and dark. If gravity were slightly stronger or weaker, galaxies might collapse too quickly or fail to form altogether. The formation of planetary systems, like our solar system, depends on just the right amount of gravitational pull to gather dust and gas into planets, while allowing them to orbit stars stably. In essence, the precise value of gravity is perfectly tuned to enable the cosmic environment necessary for life to exist. The electromagnetic force governs the interactions between charged particles. Its strength determines the stability of atoms and the ability of molecules to form. If this force were slightly stronger, chemical bonds would not form correctly. If it were weaker, atoms would not hold together. The proton-to-electron mass ratio is approximately 1800 to 1. This specific ratio is critical for the stability of atoms. Even a slight variation would destabilize matter and prevent the formation of the complex molecules necessary for life. Earth itself resides in the Goldilocks zone of our solar system, where conditions are just right for life. If Earth were slightly closer to or farther from the Sun, its surface temperature would either be too hot for liquid water or too cold to sustain it. The presence of a stable star, a protective magnetic field, and an atmosphere further underscores the precise conditions that make life possible. Even water, one of the most basic necessities for life, is completely astounding when viewed through the lens of fine-tuning. Despite its simplicity, just 2 hydrogen atoms bonded to 1 oxygen atom, water exhibits a range of characteristics that are unmatched by almost any other compound. These properties, rooted entirely in its molecular structure, create the exact conditions necessary for life to thrive. Water's ability to dissolve a wide variety of substances is one of its most important features. This is due to its polar molecular structure, which allows water molecules to interact with and break apart other molecules. In biological systems, water acts as the perfect medium in which nutrients, minerals, and gases like oxygen are transported. Blood, which is largely water, carries these essential substances to cells while removing waste products. This property also facilitates vital chemical reactions. In living organisms, water dissolves reactants and provides the environment where complex biochemical processes occur, such as the breakdown of food during digestion and the replication of DNA. Water has a high specific heat capacity, meaning it can absorb or release a significant amount of heat with only a small change in its own temperature. On a global scale, oceans and lakes moderate Earth's climate by absorbing heat during the day and releasing it slowly at night. In living organisms, water plays a vital role in regulating body temperature through the evaporation of sweat. Water remains liquid across a broad temperature range, from 0 degrees to 100 degrees Celsius at standard pressure. This broad range allows water to exist in liquid form across vast environments on Earth. Liquid water is necessary for life because it acts as a solvent and medium for biochemical processes. Without it, cells, the tiny factories of life, could not function. Furthermore, water exhibits a distinct density anomaly. Unlike most substances, water expands when it freezes. This makes ice less dense than liquid water, allowing it to float. This property is vital for aquatic ecosystems. When ice forms on the surface of lakes or oceans, it insulates the water below, preventing it from freezing solid and allowing life to survive during harsh winters. If ice sank, water bodies would freeze from the bottom up, turning oceans into solid blocks of ice and making aquatic life impossible. Water also has a remarkably high surface tension, meaning its molecules stick together strongly due to hydrogen bonding. This cohesion enables water to form droplets and allows it to move through narrow spaces, such as the tiny capillaries in plants and animals against the pull of gravity. Water is transparent to visible light, allowing sunlight to penetrate oceans, lakes, and rivers. This property is essential for photosynthesis in aquatic plants and algae, which forms the base of nearly all food chains. Water's role extends directly to its interaction with biological molecules. It stabilizes proteins, DNA, and other complex molecules, helping them maintain the shapes necessary for their functions. It is truly the lifeblood of our planet. Its properties are so uniquely tailored that they have led many scientists to marvel at the role it plays in sustaining life on Earth. Without water, life as we know it would be impossible, highlighting its fundamental importance in the story of life's existence and evolution. Dark matter and dark energy, though not directly observable, play crucial roles in the universe's structure and expansion. Dark matter provides the gravitational scaffolding for galaxies, while dark energy drives the accelerated expansion of the universe. If their proportions were even slightly different, the cosmos would be completely inhospitable to life. The sheer improbability of these precise conditions occurring by chance has led many to conclude that the universe is the result of intentional design. William Lane Craig explains, "The odds of a life-permitting universe occurring by chance are so astronomically low that it is more plausible to believe in a purposeful designer." The concept of a designer also aligns with the anthropic principle, which states that the universe's laws and constants appear fine-tuned, specifically to allow the existence of observers. Astrophysicist Hugh Ross writes, "The fine-tuning of the universe is so exact that it's as if the universe knew we were coming." The evidence for fine-tuning extends beautifully from physics into the realms of chemistry and biology. The properties of carbon, for instance, make it uniquely suited to form the complex molecules required for life. Carbon's ability to form long chains and rings underpins the entire chemistry of life, from DNA to proteins. Furthermore, the conditions on Earth that allow for the sustenance of life are remarkable. The planet's distance from the Sun, its axial tilt, and the presence of a large moon to stabilize its rotation are just a few examples of the factors that make Earth uniquely habitable. The fine-tuning of the universe compels us to confront profound questions about its origins. While some argue that fine-tuning can be explained through naturalistic mechanisms or multiverse theories, such explanations often rely on highly speculative assumptions. The idea of a designer, by contrast, provides a coherent and intuitive explanation for the universe's extraordinary precision. As we continue to uncover the intricacies of the cosmos, the evidence for fine-tuning grows ever more compelling. Whether viewed through the lens of physics, chemistry, or biology, the universe's remarkable suitability for life points to a reality that transcends mere chance. It invites us to consider the possibility of a designer who orchestrated the cosmos with intention and purpose. The question that arises from these observations is, how did the universe come to be so finely tuned? Was it simply a coincidence, or is there a more profound explanation? Even if one doesn't believe in a creation, the question remains, how did everything come into existence from nothing? If we assume that the universe indeed came from nothing, we are faced with a multitude of unanswered questions. What exactly is nothing? Is it a state of complete absence of matter, energy, and space? Or is it simply a label we use to describe something that is beyond our comprehension? Furthermore, if the universe came from nothing, then how do we explain the laws of physics that govern its behavior? Where did these laws come from? Did they emerge spontaneously along with the universe, or were they somehow inherent in the fabric of nothingness? The idea that the universe came from nothing is often seen as a more scientific explanation than the idea of a creation. However, this perspective assumes that the concept of nothing is somehow more rational or easier to understand than the concept of a creation. In reality, the idea that the universe came from nothing is just as mind-boggling as the idea of a creation. In fact, I would suggest that the concept of nothing is even more incredible than the concept of a creation. At least with the concept of a creation, we have a rational framework for understanding how the universe might have come into existence. As I pointed out in my book's introduction, the evidence leads to a compelling conclusion. A creator designed our universe, and the Big Bang marks a definitive creation event, including the inherent potential for this absolute fine-tuning. The vastness of the cosmos, the precision of its laws, and the intricate tapestry of life all point toward intentionality rather than chance. However, while the evidence suggests the reality of a universe brought into being with remarkable order and purpose, the ultimate mechanism of this creation remains, at least for now, beyond our reach. Perhaps this unknowability is by design, an invitation to embrace both curiosity and humility in equal measure. It is not a weakness to admit that the ultimate purpose of creation lies outside our current understanding. Rather, it is an acknowledgement of the profound and infinite nature of the question itself. The journey to understand creation is as much about the search as it is about the answers.